to the topic of this week. The topic of this week is very, very, very important. And this is the last topic of this semester. That is regression. Before we go to the topic, let's summarize what we have learned from the first week to the week 1 to the. Thank you very much. Thank you.
Just give me some.
Sure, I will buy a cup of coffee to you. And let's summarize. Okay, I'm still waiting for you to come back and in order to discuss the regression. Okay, so for the whole story is that from the week 1 to the week 12, what we plan to do is only one thing. We have the population, we have the sample. For the population, 99%, we don't really know the parameter of the population. But what we know is we can get a sample from the population, a part of the data from the population. And then we can calculate the average of the sample. That is X bar, the average of several numbers. And then we can use it to predict, estimate, indicate, infer the value of the mu. But the problem is we use a very small sample to estimate the parameter of a very huge population. It is wrong. Yes, I agree with you. The difference between the mu and X bar, we call them the sampling error. So you may ask me a question, if there is an error, so how can we believe the result? This is not reliable. Yes, I agree with you. You are right. So what we can do is we try to make it better. How can we make it better is we don't really use the point estimate, the X bar, to estimate the mu. We create an interval to catch the true value mu. That is what we did in the last 2 weeks. Not really last 3 weeks. The interval estimate, that is the equation. And so far, what we are doing is we just focus on only one variable, that is x. So you may thinking like maybe we can put the two variables together to calculate the correlation. Yes, we can do it. If we calculate the correlation, we can have several possibilities. For example, like we can get the correlation between x and y. When the x increased, the y is increased. Or you can get a negative correlation. When the x increased, the y decreased. So now, currently, you should know how to calculate the correlation using the formula, which means if I give you the two variables, you can calculate the correlation of these two variables. So what we can learn from this graph is that there are some information from the x and the y. And do you think it is possible for us to use the information from x to make the estimation of the y better? For example, like in this case, we found that the x bar is different with the mu because of the sampling error. So is it possible for us to use other variables, the information from other variables, to make this x bar better? And of course, several hundred years ago, somebody asked this question and tried to give some solution. And one of the solutions is a regression. What we do for the regression is we try to use the information from the x, from other variable, to make the prediction on the y better. So that is the whole idea for the regression. But before we can go to the regression, there are the two assumptions. What are the two assumptions? Sure. Before we go to use the information from the x, because from here you can see when the x increased, the y is increased. And now we want to use the x to make the prediction of the y better. There are the two assumptions. The first assumption is they have to relate it to each other. So, for example, like in here, when the rho equal to 0.00, they are totally random. And the x will be how many people buy the banana in Hong Kong. And then the y will be how many people buy the apple in Africa. So what is the relation between each other? No any relation. If there are no any relation, of course, no any information from x on the y. That is the first thing. Second one, we must have some theory to prove there are some information from the x on the y. One example is like our tutorial questions. Like how much money your parents have will decide whether you can pay the tuition fee, something like that. Or the height of the parents will decide the daughters, whether they are tall or not. But do you think how much money you have will decide who will be your parents? Of course not. Maybe you can do it, but apparently this is not a good decision. When you have money and then you will choose who will be your parent, who will be your mother, who will be your father, is ridiculous. So the second assumption is we must base on some theory for the relation between x and y. In here, there is a very common mistake. A lot of people, they put the too much on the regression. For the regression, what they can do is just use the x, or for the simple regression is only one x. For the multiple regression, we will have several x. What we do is we just make the prediction of the y better. But the regression, they never told you the relation between the x and the y. It is from the theory. We'll go through this definition later. So now the problem is, how can we make the x help us to make the prediction of y better? At the beginning, we assume we don't have we have only one variable. For example, like in here, they are how much money you pay to buy the coffee. For example, like I buy coffee from this place. Is it good? So I think the quality is not bad actually. So in here, they are the how much money I pay. I spend to buy the coffee, or the customers they pay to buy the coffee, and totally we have the 6 observation. So what we can do is we can put them on a graph, and in here you can see this is not the x. This is only from the 1 to 7, because sorry, it's only 1 to 7, but actually we have only 6 observation. So in here I just show you what is the point for each of them. Is it right? For our first observation, it's 5. So the point is here, 5. The second observation is 17. The second observation is 17 there.
What is the 17?
It's how much money I pay to buy the coffee. I mean, I not really buy the coffee. I still buy a piece of cake. Or maybe you see some student ask me to buy a cup of coffee to him. So I have to be forced to buy 3 cups of coffee, or maybe 4 cups of coffee. So that is anyway, that is the expenditure. For the 3 observation, is 11 is there. Is it right? So based on this 6 observation, currently I have only one way to predict how much money I will spend in the next week. That is X bar. That is average. Make sense? Which means we sum all of them together and divide it by 6. Well, I will get the 10. So I make this graph a little bit larger in order to show you what happened. So this red line is the y bar, is a 10, right? This 10 is from is a summary the summary of sorry, this 10 is the average of these 6 observations. And now the distance from each point to the y bar will be the, how to say, the error for my estimator, right? Because I use y bar to predict what will be happened in the next week. But based on the data in the last 6 weeks or in these weeks, we have the 6 observation. And for the first observation, I spent only $5, but I predict I should pay $10. For the second point, I predict I should pay $10. I should spend $10, but actually I spent $17. So that will be the difference between the observation to the y bar, the average of the y. Make sense? So now let's see if we sum them together, what I get will be equal to 0. So what we do is I use the yi, each point minus y bar, and then square them. The only reason for me to square them is I want to make them to be a positive value. So yi minus y bar square will be get 25, 49, and 1, 4, 16, and 25. I give you the 30 seconds to help me double check I don't make mistake in this part. I always made a mistake, so help me to check it. Yes?
$10 is X bar or Y bar.
Okay, good. So in here, I can call the coffee money to be the X or the Y. So in here, I define the coffee money is a Y. Is it okay? Or I can call the coffee money is A or B. But I'm happy to call it Y. I think that could be the only right from a lecture. I can decide what I wanna, what is the name for the variable. So I call the coffee money is a Y. And because coffee money is a Y, the 10 will be the Y bar, the average of the Y. Is it okay? So no matter you are happy or not, I'm still do this one. Call it Y. And that will be the yi minus y bar square. Is okay? And we sum them together, and we get 120. Let me give them a name. We call this equation is the sum of squares of the residue or the error. Sorry, I have to make it smaller. The reason why we call it is a residue or the error is because that is the difference between the y bar to each observation. And I square them, I call them is the squares of the residue. And then I sum them together, I call it is the sum of squares of the residue or the error. Equal to the yi minus y bar square. Make sense? So which means for this part is I have only one variable, that is a y. And that will be the sum of the squares of the residue. Now what happened is, let's go back to the beginning, is if I give you, or if you give me a variable which is related to the y, what we want to do is we want to reduce this number. If I successfully reduce 120, this number, which means I use a variable to reduce the error of the y. That is a purpose for what I plan to do in the following 2 hours. Not only 2 hours, 1.5 hours. So that is the whole story. Now let's see how can we make it smaller. Before we go to the details, let me summarize what I'm doing now. In here, the value of the y hat is a 10 for the area value of the x. For the area value of the x, I use the y bar. Actually, at the beginning I used the x, but I found I should use y. I have 6 observations of the y, and then I calculate the y bar. That is the only choice for me to predict the future. So the y bar equal to the y hat. And in here, the y hat equal to the b0 plus b1x. And we assume there is a variable which is correlated to the y, and there are some theory told me it could be useful to predict the y hat. But of course, in here I assume the b1 equal to 0. If the b1 equal to 0, what I get is the y hat equal to the b0. And in here, the b0 equal to the 10. This 10 is a y bar. Y bar equal to the y hat equal to the b0. b0 equal to the y bar. Y bar equal to y hat. Y hat equal to b0. And then b0 equal to the y bar. It's a loop. So now, what we do is we put x. We found x. The reason why I call the coffee money the y is because I want to keep the x for other variable. What is the meaning for the x is I use the income, my income as the x, and y will be how much money I want to spend. I think this is a logic decision, because if I earn a lot of money, which means I have more money to buy the coffee for you. But if I earn only like $34, no matter how do you force me to buy, I will not spend the money because I need to use them to buy the food. So which means there is a relationship between the x and y. And if I have a x and a y, I can make a graph in here. I will make a better graph when we do the simulation, but that is what I can do using my hands. So I'm not really good in this part. So that will be the point in here. What we are doing is that the x and y based on 2 reasons. First one is the x theoretically the x will make decision on the y. Secondly, the correlation in here is positive correlated. They are correlated to each other. And the theory told us the y equal to the uppercase b0 plus uppercase 1x. Which means the value of the y is a function of the x, y equal to the fx. And we call the x is independent variable, and y is a dependent variable. Which means the change of the y is depending on the value of the x. And the other way for you to understand is the x will be the income of your parents, and then the y will be your pocket money. So how much money do you have depending on the income of your parents? If they are rich, they will give you the more pocket money. If their income decreased, your pocket money will be decreased. So that in this equation we don't really know. Theoretically, we don't really know the b0 and the b1. But what we know is we try to predict find the capital B0 and B1. Use several formula. I will show you later. That will be here, the end of the whole story. In the middle of the story is Z. What we have is a population. That will be all observations we can have. For example, like let's go back to the case of the coffee money. So we can collect how much money I spent on this shop from the 2009. When I come here, it will be totally 5 years. But apparently now we cannot do it because we don't really do those work. So what we do is we have only the X and the Y. It's from the sample. The difference between the population and the sample, we call them the error term. That will be the epsilon. Epsilon is a Greek letter. That one will be the error term, or the unexplained variation in the Y. So what is the meaning for these two equations is that we have the X, we have the Y. Do we have them? Yes or no? If you say the no, I will show you right here. So that is X and Y. And based on these 6 points, can we get the capital B0 and capital B1? Maybe not. The difference is epsilon. We call them the error term. Which means if this is biased B0 and the beta 0 and beta 1 X, Y, if I give you these 4 letters, I give you the value of each of them plus the epsilon, you will get this equation. Because they are not equal to each other, we have an error term in here. And what we do is use some formula. We will get the B0 plus the B1X. And this B0 and B1 will be the coefficient of the capital B0 and capital B1. That is the relation between 1, 2, 3, these 3 equations. So what's the meaning for this equation? For this equation, that is the way we have to use it. We discussed about the relation between these 3 equations, but we never tell you how to get the value of the small b0 and small the b1, the lowercase b0 and lowercase b1. What we do is we try to calculate the mean or the expected value of the y for a given value of the x. So which means, given the value of the x, we want to predict the expected value of the y. And we assume that it is equal to the beta 0 plus beta 1x. And the reason why, if I put the expected value, the conditional probability, that is what we have learned in the week 2 or week 3. In here is because we assume the epsilon is followed with a normal distribution. And the mu equal to 0 and the sigma square. In here, the sigma is a constant number. Because the sigma follow with a normal distribution. So the expected value of the sigma equal to 0. And the expected value of this whole equation will be equal to the beta 0 plus beta 1x. So that is the whole story for the regression. And now let's go to do some simulation. Let me show you what is the meaning for this part. In the simulation, what we do is we add one like the goal of the whole story. We design everything, so we know what is the epsilon, what is the y, what is the x, what is the beta 1, and what is the beta 0. So in here, we see the y equal to the capital B0 plus B1x. And for the B0, we give them the value equal to the 1. And for the B1, we give them a value equal to the 0.5. So if I give you this, give you the b0 and b1, if I give you the value of the x, value of the y, you will have the line. That is a theoretical relation between x and y. And for this part, we assume that the x is from the normal distribution, and the sigma and the mu is equal to 1. And we generated at the beginning. Let's try the 50 observations. Okay, now we have the 50x, and that is a histogram of the x. You can see this is the value. This is the value of the x, from the 1 to the 50. And we assume the sigma equal to the 1. Sigma E is a epsilon. So in here, we assume sigma 1 equal to the 1. It's a constant number. Let's go back to the MATLAB. And we generate 50 epsilon. Epsilon is a 50 times 1 vector. We have the 50 epsilon. And now we calculated the y and the theoretical y, and we generated the mean of the y, the theoretically y, and make the plot. On this graph, what we learn is there are the 50 observations, and this red line is just based on the capital B0 and capital B1. This is a theoretical relation between the x and the y. And the blue line is x bar and y bar. So now what we do is, I don't tell the computer, let's play the game with the computer. We don't tell them the theoretical y. What we tell them is that we just give them the y. You can see the y is based on the 3 parts. B is based on the first one is 1 plus the x times beta 1 plus epsilon. This epsilon is error term. We deliberately put them into the y. Because we want to play the game with computer, we try to see, like, we try to hide the parameter, and then ask the computer to help us find the parameter. So now, what we give the computer is only the x and y, and all of them is the equations for the computer to calculate the beta 1 and beta 0. And after that, let's see what we get. Oh, that is what we get from the computer. This red line is a theoretical relation between x and y. We know them. We design the code. So will be the y equal to the 1 plus 0.5x. And for the black line is the estimated relation between x and y. They are not really exactly equal to each other. The difference will be the epsilon. So that is what we have proved. And for the blue line in here, this is the x bar and y bar. It is across the estimated line. So the red line will be y equal to the capital B plus capital B1x. And then we put some epsilon into to create the y. we know the epsilon, we know the y, we know the y, sorry, we know the epsilon, we know the x, we know the beta 1, we know the beta 0, so we get the y. And then what we do is we put the y and the x, we give the computer the y and x, ask them to calculate the value. Finally, they give us the y hat equal to the b0 plus b1x. That is the whole story. This is a red line. This is a red line. This is how we generate y. This is a black line. The only thing we don't discuss is, if I give you x and y, how can you give me the b1 and b0? Before we go to talk how to get b1 and b0, let's go back to here. Have a look again. We have the red line, capital B0, capital B1. We have the black one. Black one is estimated equation. Y hat equal to the B0 plus B1x. And you can see, actually, if we know the B1, we can know the B0. If I give you the value of the x, and give you value of the y, and give you the value of the beta 1, actually you can find the value of beta 0, right? So that is how we get the beta 0. Now the problem is how we get the beta 1 first. The b0 equal to the y, the average of the y, minus b1, the average of the x. Because the x bar and the y bar is on the line, on the estimated line. Now the main problem is we need to get the b1. The b1 is based on this equation. For the b1, that is the slope of the line. So how can we find out the slope of the line? The first part will be based on the change of the x bar times the change of the y minus y bar. So that is in here. For each data point, we take the xi minus x bar, and then we change we take the y minus y bar, and then we time them together, the 2 and 3 together. And finally, we add up all of them. Let's ask, give this part a name. We call them the SS XY. That'll be easy for me to put them into the computer, actually. And this part will be the xi minus x bar square. For the denominator will be equal to for each data point, we take the xi minus x bar, and then we square them and add all of them together. We'll get this part. We call them the SSXX. In here, you may ask a question, why do we do that one? The reason is very simple. Let's go back to the simple correlation coefficient. And during the workshop, I think all of you has already tried how to calculate the simple correlation coefficient and how to run the regression. So in here, what we have discussed is just the calculation behind of the command of this data. So that is what we have already discussed in should be week 3 or week 4. The correlation will be equal to the change of the x times the change of the y divided by the standard deviation of the x and y. And what we are doing in here is exactly the same. The only difference is we kick out this part. And that is the way we get the b1. And in here, the b1 equal to the 615 divided by the 4,206. and the B1 will be equal to this value. And then when we have the B1, we'll get the B0 will be equal to this part. So let's try it to see whether the formula is work. Let's go back to the code. In here, we get the size of the x will be equal to the n and the k. And because x is only a vector, is only a 50 times 1 vector. That is the value of the x. So in here, k equal to the k times k plus 1. This 1 is the intercept. And this is the calculator of the x bar and y bar. And the alpha we'll discuss it later when we're talking about standard deviation. So in here, what I'm doing is we calculated the SSXY and XSXX. So in here, I use x minus x bar. X is a 50 by 1 vector. And average of x times 1, and this is a 50 by 1 vector, will be the each x minus average of x. And this is a little bit tricky, but it's not really very fancy, just a way to calculate the summary of this part. That is, we use this vector times this vector. It's a column vector divided times a row vector. And then we get the SSXY, SSXX. And the beta 1 equal to the SSXY divided by the SSXX. And the beta 2 equal to the average of y minus beta 1 times the average of the x. So which means we get beta 1 and beta 0. And let's display them to see whether what is the value we get. And in here, the coefficient will be equal to the 0.83 and 0.61. And let's check. Okay, so before we check it, we have to use the right data set. What I'm doing in here, this is exactly same to the simulation, but the only difference is I kick out the simulation part. And currently we are using this data set. And let us to try what is the result. We have the 5 observation in here. So that is a plot for the 5 observation in here. And this is an estimated line. And for the coefficient, will be equal to the negative 0.82 and 0.14 and 62. Let's check whether I made a mistake in the calculation. So in here, the B1 equal to the 0.1462. And the average of 10 and average of the x is 74. There will be the B1 and that is the B0, that is B1. So now I give you the 30 seconds to find the value of the B1 and the B0 to check whether it is exactly same from the computer. Is okay so far? Oh, I mean, you can calculate the value of the B1 and the B0. They will be exactly equal to the value from the computer. Yeah. So it makes sense for you for the regression. All good? you have any question, problem? Or you are already lost from the beginning? This part is a little bit tricky, so try to follow with me. If you are lost, please give me a signal, and then I'm very happy to repeat it again. So what is the problem? Do you have any problem? Which part you are confused? Try to ask some question.
Yeah, I don't know what to ask. I just got lost.
Where you are lost?
Yeah, the computer was here.
Oh, okay. Let's repeat it from the beginning, and this time without simulation. The whole story is that at the beginning we have only one variable. We call them the y, because I want to keep the x for other variable. And for the y we have the 6 observation, and we can make the plotting here. The reason I make the plotting here is currently the only way for me to calculate to predict what happened in the future, or to predict the parameter of the y is only the average of the y. So that is the y bar. And they are the exactly same graph. And now we have calculated yi minus y bar square equal to 120. And we give them a name is SSR. And that for the SSR it means when the y hat equal to the B0. So now this is the worst case, which means without any information from the x. Before we can compare whether the x will make the y hat better or not, we have to find the B0 and the B1 first. Make sense? So now, how can we get the B1 and the B0? B0 is fun. B0 is not difficult. B0 equal to the y bar minus B1 x bar. Because we are pretty sure the estimated line in here will cross the x bar and y bar. So the B0 will be easy to get. But now the problem is we need to get the B1 first. The B1 is equal to this part divided by the xi minus x bar square. The reason is the B1, this equation is from the correlation of the x and the y, but we slightly modify it a little bit. This is the equation we have already discussed a few weeks ago. The correlation of the x and y equal to the change of x and y, and divided by the standard deviation of the x and y. So what we do is we kick out of this part. That will be the equation for the B1. So now in here, if you use each value of the x, 34 minus x bar, y minus y bar, y minus 10, and sum them together, you will get the SSXY. And same idea, xi minus x bar square, you will get the 4,206. And then when we put them together, you will get the B1. This B1 is a slope. Does it make sense? This is only half of the story. What we plan to do is we try to prove the x will make the y hat better, which means we need to make this value smaller. But now what we do is only half of the story. We get the B1 and B0. And for the last half story, let's have a 10 minutes break. And I give you 10 minutes to discuss your neighbors. So let's go back to the regression. We have already discussed the half of the story, and now I assume all of you have know how to calculate how to get the value of the B0 and B1. Or if you are still confused with B0 and B1, you can assume you already know them very well. But anyway, it's only some equation to get B0 and B1. So when we have the B0 and B1, and if I give you the value of the x in here, do you think you can get the exact value of the y in here? Yes or no? But please let me tell you, the answer is no. You can try. If you put the 34 into the equation, let's try it together. Let me see. Okay, the B1 615 divided by 4,206 equal to the 0.1462. So 0.1462 times 34 plus a negative 0.8. What we get is a 4.15. However, the real value for the y is 5. Why? Where is it wrong? Pardon? Where is it wrong? The difference is error is epsilon. Does it make sense? That is the equation we have in here. We have x, we have the y, we have the beta 0, beta 1, and we have epsilon. So the difference between the y minus y hat is the error. So which means if I give you the equation in here, this equation in here, for each xi, you can get a y hat. And the value of the y hat is already there. So now if we use the y minus y hat, we'll get the 5 minus 4.1 will be equal to the 0.84. Does it make sense? There are the two steps. The first step is to get the y hat. The second step is to get the y minus y hat. And if we sum the y minus y hat equal to 0, because we want to minimum the error. So how to solve the problem? The answer is very simple. We square each of them and will be not equal to 0, and then we sum them together will be not equal to 0. So that is the equation y minus y hat, and then we square them and sum them together will be equal to the 30.07. and we give the name is SSE. What is the meaning of the SSE? Sum of squares of the residue. So now you may ask a question, wait, there are the two SSE. Yes, I agree with you. So the whole story is that at the beginning we have only this graph. Is it right? We have only one variable, that is y. And we add a x in here, and we have this graph. So based on this graph, we can have a SSE y. The y, it means this is a SSE based on the y, will be equal to the 120. This 120 is without the x. And now we give them another name. The reason is because I want to use SSE in the later. So the SSEY, we call them an SST. The T will be the total. And this is SSE. And the SSE plus the SSR will be equal to the SST. Or we can thinking like this SSE is the sum of the error. Is it right? But what is the difference for these two parts? This SSE is from the residue. Yes, you are right. And then it's from the graph on the right-hand side. And this SST is from this graph. So which means this graph, this SST, it means without the x, what is the errors for the y? And this SSE is with the x, what is the sum of the errors? But actually, we can define another one is we call the sum of squares of regression. The sum of the squares of regression will be the y hat minus y bar. Why? Oh, it's because of the y. That is a good answer. The reason is y. Yes, you are right. I mean, he's very smart. So the answer is because of the y. Y hat is a estimated value from this graph. And then the y bar is the estimated value from this graph. The difference will be the reduced error from the x. Does it make sense? Y bar is without x. Y hat is with x. So y hat minus y bar will be because of the x. What is the residue? What is how many errors we reduced? Make sense? You don't need to worry about calculation. We will use the MATLAB to show you my calculation is correct. So if I can write down them I can show them, which means they are correct. So what happened is the SSR plus SSE should be equal to the SST. The reason is very simple. SSR will be the residue or the error we reduced because of the x. And the SSR will be, even we put the x into the model, but we still have some error or residue. And we sum them together will be equal to the total errors without x. That's the reason why the SST equal to the SSR plus SSE. Make sense? So now maybe we can make it a little bit complicated. How can we define a model is good or bad? The theory told us, or at the beginning, what we want to do is we want to see, like, compared with the model without the y. In here, compared with this model without the x, what is how many percent of the residue is decreased? The errors is avoid, is reduced. So will be the SSR divided by SST. SSR will be because of what is the difference between the y hat minus y bar? Or the sum of squares of the regression divided by the SST without the y. No, sorry, without the x. So that is how do you calculate the R square. And that is how we determine how good that the line from the two variables fit the data by comparing it to the SSE of this model, which you pretend the second variable doesn't even exist. So that will be the whole story. Do you have any questions, comments? Pardon? Zoom in. You need to write down them, and you can find them from the textbook. I just copy them from textbook. I try to base put my argument based on the textbook, which means if you don't come, I still suggest you to come to show up in the lecture. But even you don't show up in the lecture, when you go through the recording, you can have a textbook to go through with. So now let's summarize how many y do we have in here? We have a lot of y from beginning to the end. Now we have at least the two y. The first one is a real y hat. Sorry, the first one will be the real y. The yi will be the observed value from the beginning. Five, 17, 11, 5, 17, 11. And when we have this estimated equation in here, we can have the y hat. And when we have the y hat, we can have the y minus y hat. And we call them the error. So we can give them another name. We call the error equal to the E hat. The reason why we call them the E hat is because we want to use the E hat to be the estimated value of epsilon. Make sense? So the whole logic is that we have x and y. Based on the x and the y, we can calculate the b0 and the b1. And based on the b0 and the b1 and the x, we can have the y hat. The y hat may not exactly equal to the y. And this is y hat, this is y. And the difference between the y and the y hat will be we call them the error. And this error will be the estimated epsilon. So now, what do we have? We have the x and y. And then we can have the estimated b1, estimated b0. And based on the estimated b0, b1, we have the estimated y. Based on the estimated y, we have the estimated epsilon. Is it right? Or you are already lost? I'm pretty sure 50% of you already lost.
Yeah, more than.
That is very normal. To be honest, I mean, for myself, the first time when when I'm listening the lecture describe this part, my feedback is, what the hell? I mean, actually, he's a very nice guy. He's a guy from Europe. He's very famous. Simon is a very famous statistician. And what I'm doing is actually copy what he did. So let's go back to the beginning. For the regression, is a we have the x and we have the y. Based on the theory, and at the same time, we can find they are correlated to each other. We want to use x to predict the value of the y. Or we want to make the x to make the prediction of the y better. So now what we can do is, this is the y we have. This is the x we have. And some theory told us that is the relation between x and y. But we don't really know what is the value of the b1 and the b0. So what we know is that we can get the sample from the There will be the x and the y is in here. But we are pretty sure this beta 0 and beta 1 may not exactly equal to the b0 and b1. The first reason is the other sample is only part of the population, so there's some error. And how do we put the error? Is we put v plus a epsilon. We don't know what is exactly the value for the epsilon, but we know there is a epsilon. If I put an epsilon in here, we can have this equation. And what we do is we have x, we have y, we can find the value of the b1 and the b0. This is the formula for the b1 and b0. And when we have the b1 and the b0, we can have the y hat. When we have the y hat minus y will be equal to the e hat, will be equal to the epsilon. That will be the estimate of the epsilon. And that is what we discussed in here. And the reason why we calculate the E hat is because we want to calculate the SSR and the SSE. The reason is if we know the SSR and we know the SST in here, we will get the S squared. So what is the meaning for the SSR and the SST is the y minus y hat square in here. We try to minimum this part, and then we want to make this part is as small as possible. And let's go back to the beginning. What we want to do is we want to make sure we can have a model that is better than this graph. Is it right? Much. This is only the y, no x. And this is x and the y. The whole story is we try to make this part, the error in this graph, will be smaller than the error in this graph. So now can you tell me we do them successfully or we fail? Just from these two graphs. Okay, for the first observation, this is the error. Does it make sense? And this is the error, smaller. For the second part, this is error. This is error, smaller. For this part, for the third observation, maybe bigger a little bit. So for the first observation, this is the error. Okay, this is the error. It's bigger a little bit again. And this is the observation of the last one. And that is the observation. That is the error of the last one. Some of them is bigger, some of them is smaller. So we need to calculate the different. How do we calculate the different is SST and SSE. Does it make sense? So let's summarize. Let me put them into, see what is the meaning of the least squares. What we have discussed in the last 1.5 hours is we call them the least squares estimation, or the OLS, ordinary least squares. And what is the meaning of the OLS, or the least squares, is this equation here. We try to minimum this equation, the y minus y hat squared, y minus y hat squared. Is in here. And what we want to do is we try to make sure this part is smaller than this part. This is from this. This is for this graph, and this is for this graph. And that will be the whole story for the least squares regression. Does it make sense? If you are happy with what we have mentioned, and we need to use several ways to describe this graph. We want to design some statistics or some ratios to reflect the performance of this model. And what we do is we can calculate the SSR, SSE, and SST. And then based on the SSR, SSE, and SST, we can get the R square. Is in here. And finally, we can calculate the F statistic. For the F statistic, the main idea is we assume the null hypothesis is this model is correct. And the alternative hypothesis is this model is correct. Why? Not because of the why. What is the reason? How come? We have only 6 observations from the population. If I give you another sample, do you think you all get the exactly same equation? No. If I give you another sample, do you think you can give me exactly the value? The answer is no. Okay, so now what happened is if I give you 1,000 data set, you all give me 1,000 equations. So this is totally nonsense. It's not reliable. Yes, I agree with you. That is the problem. So now what we do is we take a step back. We don't want to prove these two values, they are exactly right. What I want to prove is, I want to prove there are some relation between the x and the y. Or we should include at least one x into the model. And that will be this case, and this is wrong. Does it make sense? Do you understand the logic? The logic is that I cannot tell you these two values, they are exactly right, because they are from the sample. So what we do is we want to prove at least the x should be included in this equation to explain the y. So how do we do it? Is we use the f-test. And that is the equation for the f-test. If we reject the f-test, which means this is wrong, If this is wrong, it means we should include the x. But what is the parameter for the x? We don't know. So now let's try to calculate the f test and the r square. We have several examples from in the textbook, and let us try one of them. Let's try the study time and examination. This is an example in our textbook, and the x will be study hours. Is it right? And the y will be it should be their examination grades. And now, the first part is we calculated the beta 1 and the beta 0. The beta 1 and beta 0 is 49 and 1.96. And let's check whether okay, that is the exam scores and study time, this example. And for this example, I already put x and y into the code, and you can double check they are correct. 1, 5, 7, 8, 10, 11, 1, 5, 7, 8. Okay, it sounds like they don't really give us the value for this example. So based on our equation, the coefficient for the x, it should be 1.96, and the intercept is 449. And now we calculated the y hat. Y hat equal to the beta 0 plus beta 1 times x. And then we calculated E is the error. And we can calculate the standard error of the estimate. And we can make the plot. That is estimated. Let me change the color of the graph. It's because I want to use the white to see the theoretical model, so I changed the estimated model to the black. So that will be the estimated line based on the data. So for each dot, they are the observations, and the black line is our estimated model, and that will be the intercept, and the slope will be the B1. And then after that, we calculated the analysis of variance. We calculated the SSE and the SSR and SST. The SSE equal to the y minus y hat. SSR equal to the y minus y bar. Y bar is the y average of the y. And then the SST equal to the y minus y bar. These three equations, they are exactly equal to the equation I have shown you. And then we have SSE, SSR, SST. We calculate SSE and SSR. Sorry, MSE and MSR. And then we can calculate the F statistic equal to the MSR. divided by the MSE. So what we are doing is we calculate SSR, SSE, SST, and then based on the degree of freedom in here, 1, n minus 2, n minus 1, we get the SSR, SR, MSE. We get the F test. And the R square equal to the SSR divided by SSE. So that is how do we get those parts. And now let's try the value. The R square is 0.97. The F calculated 5.2. Standard error for the Y will be the 14. So that is for the F statistic for the overall fit. So now let's go through what we have in here on our slides. First part is we have a visual displays of the X and the Y. This is X, this is Y. This is the scatter plot of X and Y. And for the simple correlation coefficient, it should be from a -1 to the +1. -1, it means perfect negative or correlated. +1, it means positive correlated. 0, it means no correlation. And that will be the graph for the different correlation. And how to calculate the R is based on the SS XY and the SS XX will be the standard deviation of the X, Y, and X and Y. That is how do you get the R, how to get the R value. And that is we can test whether the rho equal to 0. We don't discuss this part. We'll do them later. And that is the critical value for the correlation coefficient, the test for the significance. And now we jump to the simple regression. For the simple regression, you need to know how do we define the dependent variable. There is another name for the dependent variable, will be the response variable. And this is a Y. And the X is an independent variable, or we call them the predictor. And my suggestion is you are the Y, because your pocket money is depending on your parents' salary. So they are the dependent variable. They are the independent variable. You are dependent variable. And which one will be the X and the Y is based on the theory. The regression, they never tell you who should be X, who should be Y. So that will be the typical questions for the simple regression. And that is fit a simple regression on a Excel scatter plot. For the simple regression, they just analyze the relation between the two variables, and it specifies one dependent response variable and one independent variable. But actually, hopefully from the next week, we can go to discuss the multi-regression, which means we have more than one X in the model. And when we propose a regression model, we may have a causal mechanism in mind. That is, we call them a theory. And they are not decided by the simple regression, and we cannot assume the X is causing the Y. That is what we have already explained. And for the range of the X. And for the prediction from our fitted regression model are stronger within the range of our observed X value. And the relationship in here is may be true for the range of our observed X. But if it is out of the range of the X, we don't really know the relation. What is the meaning for this part? this is for the sorry about the typo. This is estimated model for the x and y. And you can see the value of the x is from the 2 to the 20. If I give you a if I give you a number when the x equal to 0, can we predict the y? The answer is yes. Let's try it. This is the equation we have, and so it means 49 plus 1.9 times 0 will equal to the 49, which means you don't do any preparation before the final examination. When you come to the final examination, you will get the 49. Is it right? Maybe not really right. For this case, it could be meaningful. But if we go back to the coffee money here, the x is my income, and the y will be the money I pay to buy the coffee. So if the x equal to 0, will be equal to the negative 0.8. What is the meaning for the negative 0.8? Which means if I have the income as a kind of the punishment, I have to give the cafe $0.8 per day, or I have to give them a negative value. I can't. Is it right? So which means overestimated relationship, estimated model, is just to be helpful, might be helpful during the range of the x from here to here. Out of the range, we know nothing. And actually, there is an example from the real world. That is what happened in the 1987, something like that. Oh, sorry, 1986. So this is not the firework. Okay, sorry. Some people told me this is very beautiful, but what I want to say is these are not really beautiful. This is not the firework. There are the 6 people in this airplane, and what happened is this space shuttle is totally damaged in the 1986. This is the Challenger disaster. The reason why most people believe, of course, they have several different reasons, but some people argue the reason why we have this disaster is because their estimation is totally out of their range. Their estimation, they didn't do the estimation for this part. Let me see whether okay, it should be something like here. So what is the meaning for this part is for the engineers, they try many times for the different temperature. But they don't try the temperature for a very extremely low temperature. However, at that day, when there are several reasons. Another reason is because for the American government, they really want to try it, so they want to push it. They don't do a lot of the exercise. What they do is we try to find a day to send the shuttle to send the shuttle. So that is the problem. So what we do is they test a lot, but they never test the temperature is close to the -1, the minimum temperature permitted for the lunch. So which means their estimation is not covered this part. And actually the engineers, they already told the American government to see, okay, this is very dangerous, because our estimation is never covered the -1. We are just estimated for the temperature is more than the 0. But unfortunately, the leader of this project, they don't really listen the advice from the engineer, and then they still try to launch it. And finally, where is should be the 6 people. Okay, it's here. Finally, 7 people, they have lost their life. It's a whole totally disaster. So from this story, what I want to see is that when you estimate something, when you get the estimated result, for example, like in here, this relationship, this model is only cover the data range from the 22.3 to the 4.9. If the value is lower than this, the minimum value, or the higher than the maximum value, we don't know the relationship. So now there is another problem, is how do we interpret the slope and the intercept. There are several examples from the textbook. For the first equation, this is about the sales and the advertisement. When we have this estimated regression model, which means for each extra 1 million advertising will generate 7.37 million of sales on average. There are several points you need to pay attention, and it will be very useful when you are doing the final examination. First one is the average. Second one is a unit. When you interpreting the equation, first part you have to be very careful about the unit. I'm pretty sure in the final examination, when we give you some equations, the unit will be a little bit tricky. For example, like we tell you, for 1,000 people, what happened, or for 1 million people, what happened. So if you forget the unit, and of course we will reduce your mark. So that will be the first part. Second one is from the beginning to the end. What we are talking about is just the average. So, and what we get is only on average. And then the firm would average the 268 million of sales with 0 advertising. However, for this part, this is for the intercept. However, the intercept may not be meaningful because we don't have data for the advertisement equal to 0. And may be outside of the range of observed data. So which means for the slope, that is fun. For the slope, you need to worry about 2 points. First one on average. Second one is the unit. For the intercept, you need to worry about 2 points. First one, you need to give us an interpretation of the value, of course, and then you still need to give us a warning to see this meaning is not. No, sorry, this interpretation is not very meaningful. Does it make sense? And that is the first case. For the first case, we can interpret the prediction using the regression. So now what we do is if we put the 10 million into into here, we can get a predicted value will be the 341. That will be if the firm they spend 10 million on advertising, its predicted sales would be the 341 million. That will be better, I think. So please be very careful. This is a predicted sale. It does not mean like if you really pay 10 million. This is what happened. Like for example, if I'm working in the bank or if I'm working in some firms, you cannot tell your boss, okay, to see like if you spend 10 million to do the advertisement, I will promise you you will earn 341. If you tell your boss, if you give your boss this promise, I can promise you you will lose your job immediately or very soon. So what we do is what we found is the estimated value. But actually, what we are so let's summarize what we can learn from this part. This interpretation is based on another example. We call the pipe. What is that? I forgot. Cherny fuel usage. I mean, you can find it from the textbook. And they are the slope interpretation and the intercept interpretation. And for the interpretation, it should be similar to this part. And they found that the fitted regression is y hat equal to this equation. And then the slope says for each additional hour of flight, they will consume about the 54 pounds of the fuel. And this estimated slope is a statistic because a different sample may give you a different estimate of the slope. And please make sure the sample size is very small. For the last part, what the meaning is, well, if we increase the sample size, the prediction will be better. We'll prove it later. And that is the intercept of the that is the interpretation of the intercept. The intercept suggests even if the plane is not flying, some fuel would be consumed. However, the intercept has little meaning in this case, not only because 0 flight hour makes no logical sense. Another thing is because it is out of the range. So in the final examination, I'm pretty sure there is a question to ask you to interpret the slope and the intercept. When you are doing this question, please be very careful. And finally, for the fit of the regression doesn't depend on the sign of its slope. The sign of the fitted slope is just to tell us whether the x has a positive or negative association with the y. Second part, the intercept, is not really meaningful because it is out of the range. And the last part is regression doesn't demonstrate the quotient effect. This is very, very difficult for you to prove something will be the happened because of something. And a good fit only show you the x and y, they are very together. Both could be affected by another variable or by the way the data are defined. For this part, we'll discuss them in the next week. Hopefully we can discuss them in the next week. And now for this part, when the sample size is very small, if we increase the sample size, what will be happened? Let's go back to the simulation. Currently, we have a, at the beginning, let's try n equal to the 10, which means we have a, let me try 5 first, which means we have only 5 observations here. And oh, this is so bad. We have several graphs. The first graph is value of the y, because we have only 5 observations, so that will be 1, 2, 3, 4, 5. They are not really like the normal distribution. And this is a theoretical model. It will be the red line. That should be the red line. However, this is our estimated model. Totally far from the theoretical model. We don't really catch the true value actually. And this is a residue of this model. What the meaning on the residue is, this is x. The x will be the x in the model, but the y will be the e hat. So that will be the 5 point. Now let's try 50. Will be the 10 times. Better a little bit. You see? Now let's try 500. This is much better. But you can see that the 500 observation on the graph, and the estimated line is close to the theoretical line. Let's try 5,000. For the histogram of the x, it's very beautiful. It's a normal distribution. And this is a theoretical model. And this is an estimated model with a theoretical model. So you can see actually it still be slightly different between the theoretical model and estimated model, the red line and the black line, but they are almost equal to each other. And that's all for this week. And we will go to the assumption of the regressions in the next week. And that's all for today.